Okay. So hello everyone, good morning. My name is Noam Rimock. I'm a student of Professor Yaron Oz. And I'm going to talk with you about a recent work I did with Yaron and with Chen that also we're going to talk later on about, it calls Generalized type-2 fusion of cluster states. So a little bit about what is MBQC, measurement-based quantum computing. So we have the circuit model. In the circuit model, we have, let's say, n qubits, and we do some unitary operation on those qubits. Now, doing this unitary operation is quite hard sometimes. We can build it by 2-qubit operations. But what we really wanted to do is to use only 1-qubit operation and measurements. Now, if I have n qubits and I do only 1-qubit operation and measurements, I cannot simulate anything that I can do with the circuit model. I cannot do any entanglement. I cannot create entanglement between the qubits. So the idea of measurement-based quantum computing is to first create some resource state. It's mainly a cluster state that we will talk in a minute, that is a state of qubits that is highly entangled. After I build this state, the only thing I do is measurements and 1-qubit operations, which are much more easier things to do. And also, measurement-based quantum computing is really efficient in the context of error corrections. We will just not go through it in this talk, but it's also very important to note. So MBQC is usually in the context of optical qubits. So when we use optical and linear devices, we want to preserve the number of photons. So our coding of qubits will not be, let's say we have a channel and if there are 0 photons, then it's 0. If we have 1 photon, then it's 1. Rather than that, we will take some channel. We'll say if in this channel we have polarization of horizontal, let's say this is called 0 of this channel, and else if it's vertical, then it's 1. So it's actually 2 channels that will represent 0 and 1. And cluster state, I will not get, there are some equivalent definitions. One of the definition is like that. Cluster state is graph state up to some z operations. And when I talk about graph state, I take some mathematical graph. Every vertex represents for me a qubit. I first put all the qubits on a plus state, which is 0 plus 1 over square root of 2. And then on every 2 qubits that are connected by an edge in the graph, I operate with ZZ operator, which creates some entanglement between them. It doesn't matter the order of those CZ gates because they're all commuting with each other. And this just defined to me the graph state, which is my resource state that I built beforehand. Graph state also have some generalization, which called weighted graph state, that are like graph state, but the operators that I put between 2 qubits are not CZ, but some more general operators with some parameters, Chi, When I set them all to be pi, I don't know why it was supposed to be pi here. When I set them all to pi, then I will get just the graph state we talked beforehand. Now, why I want those resource states? So the first claim is that every one-dimension cluster can simulate the evolving on time of 1 qubit. I'll take 1 qubit, I start with it here. I say, let's say this qubit on the cluster represents the qubit I want to represent. And then by doing 1 qubit operation and measurements along the way, I actually evolving in time my qubit. So I can do with that any 1 qubit rotation and I want on the qubit while he is evolving in time. If I have now 2-dimensional cluster, 2-dimensional graph state, I can think of its rows like qubits, and I can operate here with CZs where I connect two rows. And using CZ gates and single qubit operation, I can actually create, or up to epsilon create, any unitary I want. So with that, I can simulate any circuit model I want. That's why two-dimensional cluster is universal. But here's the catch. I don't just need to create this resource state. I measure it while I'm computing on it. So I need to recreate it while I'm computing. And here comes the concept of fusion gates. Fusion gates are actually some probabilistic gates that take two clusters. In some probability, it fuses them to a larger cluster. And some probability, it does not, it fails, in which we want those two clusters to remain separate, and then we will try again. So it's a way to build a large cluster from little clusters. And one of the most popular fusion gates are fusion type 1 and type 2. With fusion type 1, we build a one-dimensional cluster, and with fusion type 2, we take one-dimensional clusters and we align them together. So we are going to focus here on fusion type 2. So here you can see an example of how fusion type 2 works. Let's say we have two one-dimensional clusters. We do some X measurement on one of them and take 2 qubits of it, and it just makes them to be one logical qubit. Let's call them A and E. Now we take the qubit E from the one of the clusters and qubit B from the other cluster. We do some unitary on them, operation on the sum of its. We do. I will show in a minute. But we do some operation on them, and then we also measuring the output channels, which is actually saying we're projecting them on some state, on some 2-qubit state. Now, what will be the projection is not it depends on what we will measure after we measure them in the output states. So we have some probability to measure them in a way that the resulting state will be this plus graph, which we want to align those both to a one-dimensional cluster, and some probability it fails and they will remain separated. And specifically, what we do to the channels A and B, we get them through a polarization beam splitter, diagonal polarization beam splitter, and we measure the output modes, C and D. And we can describe it by unitary operations that transfer us from A and B to C and D. When we measure C and D, we have, again, some different possible outcomes, and with half probability, we will have an outcome in which we project onto a Bell state of A and B, which will cause us a final cluster state, and with some probability, we will create a product state, and the clusters will remain separated from each other. And in general, we can ask, may it be a different way to create a Bell state projection with higher probability? This is actually what we call Bell measurement, and it has been proven that Bell measurement has a maximal probability of half when I'm using only linear devices. This probability can be larger when I'm adding ancilla qubits, but without them, it's half. So what we did, we actually showed that there are more ways to get final state that is a cluster state by doing a projection onto a 2-qubit state that is not necessarily Bell state. It must be maximally entangled state. I will explain in a minute why. But there are more states I can project onto that will result to me to a state that is our fused cluster state up to one single qubit rotations. So this is what we call generalized fusion. It's when I'm doing some general unitary on channels A and B, and I might still get a way to get in the end my wanted cluster, maybe with a larger probability. So actually, there is a article that cited us that they did some numerical simulation, and they showed that with ancilla qubits, you can get a larger probability to the generalized fusion than to the Bell measurement. So this is actually a way to suppress the Bell measurement higher success of probability of success. But we showed that when we're not using ancilla qubits, then actually, although we have much more state to project onto, it remains the same probability, half. This is a higher possible probability. So as we said, we're doing some unitary operation from A and B to C and D. We measure C and D. We have 10 possible results. We, at first, just categorized what we can get in the end. So there are a lot of state in which we can get in the end cluster state up to one local rotation, which is good. We can also get, in some cases, weighted graph state. We can build weighted graph state. And one more thing we did, this is our analytical analyzation. For every possible final state, as depending on the result of our measurement, we computed its probability to fall to this state and its entanglement entropy. It's the entanglement entropy of the state we project onto, which is also the entanglement entropy when we divide the set of qubits to the two original clusters that we fused together. And we showed, again, that if this entanglement entropy, we require it to be maximal, then the sum of probabilities of the final states that have maximal entanglement entropy is not higher than half. And we also found all the matrices U that have this property. We also showed that when you cannot require to have entropy higher than 0 with 100% chance. There will always be some chance to get product state with 0 entanglement entropy. And finally, so we had some computations. We have some analytical result for all the probabilities of entanglement entropy. And finally, we did some numerical simulation together with Chen, and in which we asked this question. If we set some target entropy, and for every matrix U that defined as some fusion, we ask what's the probability to get this target entropy or higher, so we take the sum of probabilities of all the states that get us this target entropy or higher, and this probability we optimized over all the fusion processes. So you can see this red line here that is the optimal probability to get this target entropy or higher. So if we set lower target entropy, we have higher success of probability. And this is relevant because we have those weighted graph states that have less entanglement and entropy, so we can maybe build them with higher probability of success. And that's all. Thank you for listening.
Thank you very much, Noam. Any questions? Noam?
If I understood correctly, maybe you can kind of summarize. The idea is to find efficient ways of generating resource states or cluster states. But can you explain in what sense they're optimal, like the amount of gates you need to apply, or like what makes them?
What makes the fusion process optimal? If you have higher probability of success, in every time you do a fusion, you waste some qubits that you measure. So as long as you have higher probability of success, you using less resources in ממוצע, in average, yeah. So the higher the probability of success, the more efficient you are in using resources, in using a lot of bell pairs that you use to build this graph and then to start combining them.
Any other question? Maybe I have a question. So the assumption is that you cannot prepare the state that you really want, which is a very large state, but rather you prepare small states. Is there some kind of a threshold for what is most efficient? So I don't know what size of a state would be most efficient to prepare, because if you prepare only very small states, you will have to do many fusions.
Yeah, so this is actually a great question.
Sweet spot or any threshold for that?
So one of the questions that we don't have an answer to is what is the optimal way to create some state? As you said, maybe I want to start with a lot of small and then build them together. Maybe I want to start with some more large that are more hard to create, but then the fusion might be more efficient. We don't know. It's a great, but it's a great question.
I can make a comment on your question. It's actually related to the issue of error correction. When you try to build error correcting codes, instead of qubits, you replace them by small resource states, and then you the shape and the size of that resource state determines the threshold for error correction. So for instance, you can take like 3, 4, 5, 6, etc. And then you can ask how are they good against errors, and the threshold depends on that size and the shape of the small ones.
But you have to apply some unitaries to
The
fusion.
unitaries, as he showed, is you can try to make the best process that will increase the probability.
But this also increases some kind of an error for the entire
The probability is not increasing depending on the size of the smaller resource state. That's not, because it's a step-by-step procedure. But the shape and the size of the resource state depends the threshold for error correction.
Thank you. So let's thank Noam once again.
Thank you very much.